Oh, wait. Okay. All right. Hi, everyone. Welcome to the first seminar of Winter 2025. Happy New Year to all of you. Hope you had a good holiday break. Today, we are going to start with a bang. We have two very exciting talks. We have Wes Holiday presenting his work on margin invariance and ordinal margin invariance of voting rules. And then later, we'll have Surush Abadian presenting his work on policy aggregation. So without taking much time, Wes, the floor is all yours.
All right. Thank you so much, Nasarik, and also to Dominic for the invitation. I'm honored to be here. So what I want to do this morning is I want to talk about two theorems from two papers. So the first is in joint work with Yifeng Ding and Eric Packett. And this is a draft that we just posted on the archive called Characterizations of Voting Rules Based on Majority Margins. And the second is a short paper from last year called An Impossibility Theorem Concerning Positive Involvement in Voting. So let me just start with some framework setup. I'm in a standard kind of voting theoretic setup. I've got first of all, an infinite set of voters and candidates, but any given preference profile is only going to use finitely many voters and finitely many candidates. And I'm going to assign to each voter a strict weak order on the set of candidates. Although for my first theorem, I'm going to focus just on the linear profile case. One thing that's important is I don't really need to be in this variable candidate setting where different preference profiles can have different sets of candidates, but I will need to be in the variable voter setting where different preference profiles can have different sets of voters. So I'm going to write V of P for the set of voters in the profile and X of P for the set of candidates in the profile. And the two key definitions for setup is this hash P function. Given two candidates A and B, hash just tells us how many voters strictly prefer A to B. Okay, that's my notation, sometimes called the support for A over B. And then M sub P is the margin of A versus B, which is just the number of voters who rank A above B minus the number who rank B above A. So this is a margin of victory in the case where A beats B head-to-head, otherwise a margin of loss. Okay, so what is a voting rule for the first part of the talk? It's just a function from some set of profiles to some non-empty set. And what that means is, for the purposes of the first half of the talk, whether the voting rule outputs a set of candidates, a binary relation on the set of candidates, a probability distribution on the set of candidates, none of that matters. The output type does not matter. Okay. Now, first I want to talk about margin invariance. And as the name suggests, a voting rule is said to be margin invariant or margin based if for any two profiles in the domain of the rule, if they induce the same margin matrix, then the output of the rule must be the same for those two preference profiles. Okay, so there's been other terms used for this. Pairwise has been a term that's used for this. C1.5 has also been used for this, but I don't recommend that term. I'll come back to C2 later. And first of all, note that many Condorcet voting rules, for instance, minimax, ranked pairs, beat path, river, split cycle, stable voting, weighted covering, all C1 methods, these are all margin-based rules. And even the Borda count, at least when you look at linear profiles in the standard formulation of Borda count, is also a margin-based rule. Non-examples would be things like plurality voting, instant runoff voting, Coombs, and Buckland, where it's not enough information just to know the head-to-head margins between candidates. You need to know more about the preference profile. Okay, now I would say that being margin-based, at least coming from mathematical logic, this is a natural invariance property to at least consider. But whether it should be regarded as normatively compelling in any way, I think is less clear. So what our project was to try to characterize the class of margin-based rules using axioms with somehow clearer normative content that look more like other kind of voting theoretic axioms that we see. Okay. And in the talk, I'm only going to talk about the case of linear profiles, so voters don't submit any ties in their rankings, but we cover the general case in the paper. Okay, and it turns out in the linear profile case, we just need two pretty simple axioms, or turn out the conjunction of those is equivalent to being margin-based. So the first axiom is what we call preferential equality. So we say that a voting rule satisfies preferential equality if for any profile in its domain and any two candidates X and Y, if there are two voters who both rank X immediately above Y, so XY, XY, then either one of them unilaterally changing to Y over X will have the same result. The output of the function will be the same in PI. That's where voter I is the one who makes the flip of adjacent candidates, X and Y, or PJ, where J is the person who makes the flip of the adjacent candidates. This has exactly the same result. Okay, that's preferential equality. The idea is that we treat each voter's preference for Y over X as equal. Okay, that's the term. Now I can state an equivalent coalitional version if I assume something about the domain of the voting rule. So say that a domain of profiles is rich if it's closed under the operation of flipping adjacent candidates in a ranking. So that's a rich domain. And then I'll say that a voting, this is just a fact now, that a voting rule on a rich domain satisfies preferential equality if and only if for any coalitions of equal size, capital I and capital J, suppose that all those voters rank X immediately above Y, then if you take the coalition capital I and have everybody flip XY to YX, that has exactly the same effect as if you take the coalition J and have everybody flip XY to YX. So you're treating the preferences of these two different coalitions with respect to XY equally. Okay. So that's preferential equality in the coalitional version. And I just want to show you how this can be violated. I'm going to show you in the case of instant runoff voting. So here, let's just consider this hypothetical election between a Democrat D, a moderate Republican M, and a more extreme Republican R. And these are the percentages of the linear orders that were submitted. And the first thing to notice is that according to instant runoff, R wins. And that's because the candidate with the fewest first place votes is the moderate. So the moderate gets eliminated, and then the Republican wins head to head. Okay. But now what I want to do is consider two hypothetical ways that we could change the preference profile on the top. The first hypothetical way is these 3% of voters who rank DRM, they could flip RM to MR. So they would effectively join the first column. So that's why I zero out the second column, and now I have 40% of voters in the first column. That's one thing that could happen. The other thing that could happen is that 3% of these voters who ranked RMD, they could flip RM to MR. So they're doing exactly the same flip. That results in the preference profile on the lower right. Okay, so I have two coalitions of equal size, 3%. The Democrat 3% could flip, or the Republican 3% could flip. And on the left, again, IRV is going to do the same thing, eliminate the moderate in the first round, and then the Republican will be elected. But on the right now, it turns out that IRV changes its answer so that the Republican gets eliminated in the first round, and then the moderate beats the Democrat head to head. So what this means is 3% of Republicans have control over whether we get the more extreme candidate or the moderate, but 3% of Democrats cannot affect this choice. And that's a violation of preferential equality. Okay. And in the paper, we also study like how often could this happen in real elections? Of course, it's inherently counterfactual notion. You ask, could some coalition have made a change so as to get a different outcome than if some other coalition had made the same change? But we analyze the existing data on IRV elections, and we find that this could, in principle, happen a lot. Okay, so that's the first axiom, is preferential equality. The second axiom is due to Donsari, and it's called neutral reversal. And it says that if one profile, P prime, is obtained from another, just by adding two voters with fully reversed linear orders, then that does not change the election outcome. So the idea is fully reversed linear orders you could think of as balancing each other out. doesn't change the election outcome. Okay, so that's the second axiom. And our result for linear profiles is that those two axioms are precisely equivalent to being margin-based. Okay, so one direction is easy, that if f is margin-based, it's very easy to see that it satisfies preferential equality and neutral reversal. The interesting case is, of course, the other case where you assume that a voting rule satisfies these axioms, and now you have to argue that it's margin-based. You have to pick up two preference profiles that induce the same margin matrix, and you have to argue that your voting rule would give the same answer in these two profiles. And so for the details of that, please see the paper. But the upshot of this is basically that you can think of margin invariance as capturing some notions of equality or balancing between voters. So preferential equality, as the name suggests, that's some notion of equality. Either of two voters switching xy to yx has the same effect. And then neutral reversal is this notion that people with balanced rankings, with reversed rankings, balance each other out. Okay, now in the paper, we also dropped the linearity assumption. So we characterize margin-based methods over all profiles that allows ties. And of course, very important for practical purposes is truncated linear orders, which you can think of as a strict weak order with a tie at the bottom. Another thing we do in the paper is we consider C2 rules. And a C2 rule is just a rule whose output only depends on the hash function, the number of people who strictly prefer A to B. Whereas margin-based only looks at the difference between the number of people who prefer A to B and BA. Okay, so we look at C2, and then we even look at what we call head-to-head rules, an even larger class, which is your answer is allowed to depend both on the hash function and the number of voters in the profile. Okay, and over strict weak order profiles, these are interestingly different notions. And what we show is you can get from head-to-head to C2 by adding an axiom that we call neutral indifference. And you can get from C2 to margin-based adding an axiom that we call nonlinear neutral reversal, which is basically just neutral reversal for strict weak order profiles. Okay, so that's all I want to say about margin invariance. Let me get to ordinal margin invariance. So for a profile, let's say the majority graph of the profile is the directed graph whose set of vertices is the set of candidates. We have an edge from A to B whenever A has a positive margin over B. So this is just the normal notion of majority graph. But what I want to do now is add a binary relation on the set of edges of the majority graph, which are just ordering the edges by the size of the margin. So edge AB is stronger than edge CD if the margin of A over B is greater than that of C over D. So that's what I'll call the ordinal margin graph. And then ordinal margin invariance simply says if you have two profiles, the same ordinal margin graph, then you have to give the same answer. Okay, so here's just an example, two preference profiles. They induce the same ordinal margin graph. The numbers getting bigger means that margin is stronger. So we would have to give the same answer in both profiles. Okay, now for the rest of the talk, I'm not talking about arbitrary voting rules. I'm just talking about social choice correspondences, by which I mean a function that assigns to any profile. So here I'm building universal domain in. All the theorems will also hold for linear profiles, but let's just go with this definition. Assigns to any preference profile a non-empty set of candidates. Okay, we would like that to be a small, maybe a singleton set, but of course we can't always have what we want. Everybody on this call is familiar with what the Condorcet criterion is. Let me just point out that most of the margin-based Condorcet social choice correspondences are in fact ordinal margin-based. So all the ones that I listed before are actually also satisfy ordinal margin invariance. There are some exceptions like Kemeny or Black's. And of course, you know what the Condorcet loser criterion is as well. Now, building on work of Moulin, work of Perez and others has shown that there's this deep tension between the Condorcet winner criterion and the following variable voter axioms. The first is called positive involvement, which simply says if in an initial preference profile, candidate X wins, and then you just add a voter who ranks X uniquely first, then X should still win. That's the idea. Okay, it's a plausible sounding axiom. I don't want to say it's sacrosanct, but it's certainly plausible sounding. And the negative involvement says that if in an initial profile X loses, and then you add a voter to the profile who ranks X uniquely last, then X still loses. That's negative involvement. Okay. Now, there are some Condorcet social choice correspondences, not many, that satisfy both of these axioms. So the only sort of standard ones are minimax and split cycle, to the extent that that's standard. So this naturally leads to questions about stronger impossibility theorems, which is where I'm heading. Now, one way that it's often easy to satisfy a lot of axioms is to use a very irresolute social choice correspondence that often picks multiple candidates. So to kind of rule that out, let's add some notion of resolvability, which can come in two forms. Single voter resolvability says whenever you have a profile with multiple winners, you can always break the tie by adding some one voter with some one ranking. That's what single voter resolvability says. And asymptotic resolvability says that for any number of candidates, in the limit as the number of voters goes to infinity, the proportion of linear profiles that have multiple winners goes to 0. So like the probability according to the impartial culture of multiple winners goes to 0. Okay, so if you draw a table with some standard voting rules and classify them according to these axioms, you see that of the axioms that I've mentioned, positive involvement, the Condorcet criteria, resolvability, and ordinal margin invariance, none of the rules satisfy them all. So the obvious question is it possible to satisfy all of these axioms? And that's what the theorem says. There is no social choice correspondence that satisfies positive involvement, the Condorcet criteria, resolvability in either form, and ordinal margin invariance. So this explains why empirically we don't see any of these rules, of course, in the literature. I should say positive involvement can be replaced by negative involvement. Only 4 candidates are needed for the impossibility result, even though I stated everything in this variable candidate setting. Already for 4 candidates, the impossibility kicks in. Now, of course, when we face with an impossibility theorem, we say, like, what's the most natural axioms to drop? And at least the one whose normative status is perhaps least clear, although there's things to be said in its favor, is ordinal margin invariance. So the natural question is, if we drop ordinal margin invariance, do we get a possibility result? And so for this, I have some conjectures based on work in progress. The first conjecture is that if a similar impossibility result, I believe, will hold with margin invariance. I don't have a proof of this yet. I have a plausible proof strategy, so I could take this back tomorrow. Where I replace for now resolvability with what we call quasi-resoluteness, which just means in any margin graph where all the margins are distinct numbers, then you pick a unique winner. And in practice, all the Condorcet social choice correspondences that are resolvable, that they also, or at least many of them, have this quasi-resoluteness property, like ranked pairs or beat path or minimax. But I think I can show that this package of axioms is inconsistent. We'll see. But I also think that if you drop margin invariance, then there is, I think, a social choice correspondence that satisfies all these axioms. I have a candidate rule. The problem is it's proving difficult to prove the resolvability axioms, even though there's a lot of computer simulation evidence that it satisfies single voter resolvability. I still need to clinch a proof of that. The one interesting thing about this rule that satisfies these axioms is the computational properties are bad. I mean, I don't have a proof of its worst case computational complexity, but I certainly can't show that it's polynomial time. And so one open question that I think is interesting is, can you satisfy these axioms together with polynomial time winner determination, as the size of the profile grows? Okay, so I'm ready to conclude here. Broader picture, these are not the only invariance properties, margin invariance and ordinal margin invariance. So you can ask the same questions for other properties. Are they equivalent to some nice package of axioms, or are they inconsistent with some nice package of axioms? So here are some other invariance properties where we could do the same exercise. And of course, as you get to stronger and stronger invariance properties, like with C1, I think it's fairly implausible that you're going to find some really normatively compelling package of axioms that's equivalent to C1, because C1 just seems too strong. But I do think this project is useful of trying to re-axiomatize the invariance properties so that we can see where the boundary between plausible and implausible invariance properties lies. So thanks so much for your attention. I can't wait to hear your feedback.
Right. I had a question, but Eric already answered that in the chat. Bill has another question. Bill, do you want to go ahead and ask?
Well, I had a remark, which is that I think that bringing up this reversal property, what did you call it again?
Neutral reversal.
Neutral reversal is an interesting question because from a normative point of view, if you
Yeah.
consider an election in which, say, 1,000 people have one ranking, 1,000 people have the opposite ranking, and one person has a third ranking, which is slightly closer to one of the two groups than it is to the other, then which ranking should win the election? Of course, this property says the one voter should win this election. And it seems to me that's implausible in the sense that many people would react, hey, that's not right. And people haven't really thought very much, as far as I know, about the difference. I call that, I would say there's an argument for the large group that's slightly closer to the outlier. I call that the tipping property. But I think further consideration of this axiom from a normative point of view might be quite interesting. That's my main remark.
I totally agree. And by the way, if my conjecture is true that margin invariance is inconsistent with this package of otherwise like appealing axioms, then we would want to know, is it neutral reversal? Is it preferential equality? Is it both together? We may be able to drop neutral reversal, but still have a rule that satisfies preferential equality together with the other axioms. So I think that's a great point, Bill, that we should scrutinize the normative status of neutral reversal.
Did you also have another question?
I did have another question, which was, it seems to me there may be space in the range between margin invariance and ordinal marginal invariance. Have you thought about invariances that fit in between and whether any of them are interesting from?
Yes, a little bit about some kind of, what do we call it, affine. If you can transform one margin graph into another, so something strictly in between the two. And the reason I was thinking about that is that when I got the impossibility theorem for ordinal margin invariance and these other nice axioms, of course, the first thing I thought is, can I weaken just a little bit? Not going all the way down to margin invariance, but some intermediate notion. But nothing really systematic, Bill.
I was thinking loosely of the fact that you have more information if you know which linear combinations of certain margins exceed which other margins, right? And you could place a bound on the constants used to define the linear combinations, and maybe there's a natural bound here somewhere.
Yeah, great question. Let's add that to the research agenda.
I have one question. So a couple of years ago, I had a paper about letting voters express kind of intensity of their preferences. So we usually say I like A more than B, but then I like B greater than C, right? So kind of like showing that there is a slight stronger intensity of preference there. And of course, I'm divorced from the axiomatic world, so the paper was more on the distortion approach. But I'm wondering if people have axiomatized, designed and then kind of investigated axioms for preference types that are slightly more expressive than linear orders like that.
Yes.
Not just like the weak orders, but also something like this.
Yeah, where you can say my preference for A over B is stronger than my preference for C over D.
Right. Yeah.
Like an individual voter. So an individual voter could submit basically like an ordinal margin graph.
Exactly. Something like this, what I just pasted in chat. That I like A more than B more than D, but like the B C difference is not as much as like the A B difference or the C D difference for me.
Right. So maybe that's not as expressive as you submitting your ordinal margin graph. That would be even more expressive, right?
Yeah.
At least as I'm looking at the chat, I don't think
that
in this
would
format
like go all the way to cardinal
ordinal
utilities,
margin matrix, but
right.
I mean, yeah, you could go all the way to cardinal utilities, but I think that there's the thing that you put in the chat where you can say that my preference for A over B is stronger than my preference for B over C. I guess, and does this mean, by the way, what you put in the chat, that like your preference for A over B is of the same strength.
Same as yeah, I mean you can interpret it as that. Yeah, let's say there are only two.
And then you could also add 3 inequality symbols.
Yeah, you can.
Okay, so then yeah, I see.
Have people
The
done
only
that?
thing you can't do is you can't have cycles and so on in your preference. So
Yeah, you cannot.
you're submitting linear ordinal margin
Still
graphs.
linear order, but yeah, you are showing stronger intensities at some places. Have people looked at axioms for that?
I just saw a paper like on the archive that popped up within the last week or two about precisely this kind of setting, but I didn't actually open the paper to see what the results were, but we should revisit that. That's a great point.
Okay, very interesting. Any other questions? If not, then we are going to now do our breakout rooms. Thanks, Wes, once again. And for the just a reminder that the breakout rooms are going to be there for 10 minutes. Feel free to chat amongst each other, and then I will broadcast a message when the rooms are about to close, and then we'll come back here for the second talk, which will also be a 20-minute talk followed by Q&A. All right. Okay, welcome back everyone. So now we are down to our second talk of the seminar, and this is by Surush Ebadian, who is going to talk to us about policy aggregation. So Surush, take it away.
Thank you, Nisarg. Do you see my screen?
Yep.
Okay, great. Just a second. Okay, so hello everyone, and thank you all for being here today. And thanks to the organizers for inviting me. My name is Soroush Ebadian, and I'm a PhD candidate at the University of Toronto, working with Nisarg Shah. And today I'm going to talk about policy aggregation, which recently appeared in NeurIPS 2024, and is joint work with Parand Alizadeh Alamdari. She is also a PhD candidate at the University of Toronto and the Victor Institute, and Ariel Prokacha from Harvard. As members of the computational social choice community, we are very familiar with the aggregation part of the title, but what do I more specifically mean by policy here? Okay, so in this work, we consider the problem of AI value alignment with diverse human preferences in a reinforcement learning setting. Suppose we want to build an autonomous agent that interacts with a dynamic environment based on a policy. So in every state of the environment, our agent acts according to its policy and receives some reward, and the environment changes as an effect of this action, moving to the next state, and this process continues. So a policy is just a mapping from states to distributions over actions that the agent takes, and it determines how the agent behaves in this dynamic environment. Now, we want this agent to be aligned with human goals and values, but how do we do that? Like, one approach might be to learn desirable behavior from a single individual by observing their actions in the environment and encoding those behaviors as rewards and give it to the agent. But however, I mean, this is where it gets interesting for social choice theorists. Consider that different individuals might have different objectives for how the agent should behave. Like, one person might prioritize speed, and another person dislikes the robot being noisy and is willing to sacrifice the speed for comfort. And each of these preferences can be encoded as different rewards in our environment. And I mean, more fundamentally, I mean, society has diverse goals, values, and cultural perspectives. And these values can conflict on many topics, and they're all valid, and we cannot disregard them. And this naturally leads us to the central question in our work. How do we aggregate these diverse preferences into one collective policy that the AI agent follows? And very related to this topic, I mean, the need for considering diverse values and preferences in advanced AI models like large language models is getting increasing attention. I'm just mentioning a few works here that emphasize on value pluralism in AI alignment. On the left, we have two position papers, first from Vince Konitzer and Bill Zwicker, also in the audience, and co-authors, who argue that social choice should guide AI alignment in dealing with diverse human feedback. And also Sorensen et al. provide a roadmap to pluralistic alignment. We are also seeing industry initiatives such as OpenAI's democratic inputs to AI and the collective constitutional AI by Anthropic. So, but coming back to our work, we want to address an interesting challenge that bridges reinforcement learning and social choice theory. We want to aggregate individuals' policies into a desirable collective policy. And let me describe it more concretely. We start with the common assumption that the environment can be represented as a Markov decision process, and I'll define this formally in a moment. And the key twist is this: in our environment, in our single environment, each individual has their own reward function, and that incorporates their values. And this leads each person to have their own optimal policy. So now let me formalize our setting. We start with the standard components of the Markov decision process and MDP. We have a set of states, a set of actions, and if we are in a state S, perform action A, then with some probability we're going to end up in the status prime, and this is encoded in the transition probability function, which we assume that we have the full information of. And there's also a discount factor that we'll see shortly. And we have multiple rewards. Each agent has their own reward function, which is just mapping between the state and actions to a reward. It can be positive, negative, any real value. And for each individual I, we can, and a policy pi, we can determine the expected cumulative discounted return of a policy like this expression. So in each time we are getting some reward and we are discounting the future rewards, and we just take the sum. Okay. Now, how should we aggregate these reward functions? So one naive answer is to simply maximize the utilitarian welfare. That is, we can compute the optimal policy for the sum of rewards. But besides not being fair, this has a serious shortcoming, and that is it is very sensitive to affine transformation of rewards. So if we multiply one person's reward function by like 100, then their preferences would suddenly dominate the solution. However, an individual's optimal policy is invariant to positive affine transformations. Like if you multiply someone's reward by 2 and then add 1 to every state action pair, then their preferred policy doesn't change. And more broadly, economists and moral philosophers have long been skeptical about interpersonal comparison of utility, like Hammond noted in his work in 1991. So if different people might use vastly different scales, how can we meaningfully add these together? And to develop aggregation methods that are invariant to affine transformations, we'll look to social choice theory, where we typically deal with ordinal preferences and rankings over alternatives. And the key insight is that these rankings remain unchanged after affine transformations. So if you have a utility function that is inducing these rankings, scaling or shifting these utilities doesn't change the preference order. And this invariance is exactly what we need. So the question becomes how to adapt these ordinal rules for policy aggregation. And the challenge is that we have an infinite space of policies rather than a finite set of alternatives. So to answer this question, I need to define this key concept in MDPs. So let me describe state action occupancy measures step by step. So suppose we're at time t0. If we have the transition function, we have the policy, we can determine what's the probability of taking action A in a set S at time 0 based on this information. And we can do the same for each future timestamp. What's the probability of visiting this state action pair at time t? Then by just taking the discounted sum of these probabilities, we get the state action occupancy measure. And so it's a distribution over state actions. And the interesting thing is that this is a fundamental result in MDP theory that tells us that we can express the expected return as a dot product of reward function and the state action occupancy measure. Okay, but maybe more importantly, all these occupancy measures, they form a polytope. So any point in this polytope would be, you can construct a policy for it. And any policy, as we saw, just has a state action occupancy measure. So we can restrict our attention to this polytope somehow, and let's do voting over this polytope. So what we are saying is that let's take the set of alternatives to be this continuous space, this polytope, this occupancy polytope, and do voting over. And how are the preferences encoded? They're encoded by this reward function. Each individual has a directional preference by their reward function, and the dot product is showing the expected return of that policy for this agent. Now, based on this geometric interpretation, we can redefine ranking. So previously we didn't have any rankings for these policies for this continuous set. Now we can redefine ranking for this continuous set. How? And we can say the ranking of a policy is the volume of the subset of the polytope with the higher return compared to the whole polytope. So in other words, if you have a uniform distribution over this polytope and sample one policy from this polytope, what is the probability of observing something more, something valued more for this agent? I think this is a good place to pause a little if anyone has questions.
I posted a question in chat, but it's more of a discussion question for later.
Yeah, maybe if something is unclear, like how we are defining the ranking and all. Okay, I'll continue. Okay, so now we have the ranking. Let's redefine, let's adapt some ordinal rules. We investigated two classes of aggregation methods, one inspired by fairness notions and one voting rules, and specifically positional scoring rules. Okay, as a warm-up, let's start with the notion of proportional veto core by Moulin. The idea is that any coalition has a veto power proportional to their size. And an alternative is in the proportional veto core if they're not blocked by any coalition. And what do we mean by block? Like, suppose we have 5 agents and 2 of them come together and block this gray area in the polytope that is annotated by O1. And how can they block it? Together, they unanimously propose 60%, so 1 minus their veto power, 60% of alternatives. And this pattern area O2, they both prefer every candidate in O2 to every candidate in O1. So no policy from O1 should be selected because these 2 people are blocking it. And if some point, again, is in the proportional veto core, then it should not be blocked by any coalition. Now, the question is a proportional veto core always non-empty? And we can build on the recent result of Chudhary et al., who extend the proportional veto core to continuous settings and show that it is non-empty. Like if you slightly relax the definition by some epsilon, then it is non-empty. And we can have algorithms, simple algorithms to find one such point. There can be infinitely many, I think, because it's a continuous set, there can be different points in the proportional veto core, but at least one of them can be found in this manner. Like take the polytope and sequentially let each agent eliminate 1/n of the polytope. And then the last point would be in the proportional veto core. But I mean, this is an easy algorithm, but for computing it, we need a subroutine that measures the volume. Like in order to find that hyperplane that cuts the polytope, we need to measure that the space that we are eliminating has a volume of 1/n of the entire polytope. And that is typically a difficult problem. It's a sharp p-hard problem, but there are randomized approximation algorithms that run in polynomial time for this task. So, and this is very important. Like we are using this subroutine, this volume computation subroutine in almost all the algorithms or methods that are in this paper. Now that was for proportional veto core. Now let's move to quantile fairness. This is another fairness notion, and which was recently proposed by Babichenko and co-authors for the setting of fair division of indivisible goods. And the idea is this: suppose we have n people, m goods, then how many allocations do we have? N to the power of m. Rank all of these allocations, these n to the power of m allocations, and then we want to find an allocation that has the minimum maximum rank, something like that. Like we say an allocation is Q quantile fair if it's in the Q quantile, it's in the top Q fraction of the allocations for every agent. And one of the results of this paper is that assuming the Erdős matching conjecture, a 1/2 quantile fair allocation always exists. So the interesting part is that this is a constant and this constant is feasible. And we can easily adapt this notion to our setting. Like we can say a policy is Q quantile fair if every individual ranks it among her top Q fraction of the policies. So the problem is, at least the notion is easy to define, but does it exist? Like what is the bound? What is the quantile that we can guarantee? The problem becomes easier, much easier for the continuous setting. And we can show that there always exists a 1/E quantile fair policy. And this is tight. Like I'm hiding some, I mean, the bound in the paper is more than once, but roughly it's 1/E. And the proof is a result of Grunbaum inequality from the 60s. So if you take the centroid of a polytope or any convex body and then pass a hyperplane through that, so cut the polytope into two pieces by passing any random hyperplane through that centroid, then any part would have a volume of at least 1/E and at most 1 minus 1/E. Okay, so if we take the centroid point in this polytope, it's going to be 1/E quantile of everyone. And it's not even taking the reward functions into account. So similar to what we saw with the rank, we can define quantile. If the definition of quantile is a little, I've not mentioned it here, but quantile would be like 1 minus rank. And for computation, so that was for existence, and for computation, we can try to aim to maximize this optimal value Q star for which a Q star quantile fair policy always exists. And this can be also simply done like by binary searching over this optimal value. Then the problem becomes solving a linear program which is asking, is the intersection of some hyperplanes non-empty or not? But again, there's one important subroutine here that we are measuring. We are using that volume computation subroutine many times. Like I'm hiding some details here, but that's the hard part. That was for fairness. Now let's move on to voting rules. I'm only going to talk about positional scoring rules, and we are very familiar with it, but just to briefly mention it, like we have a scoring vector we want through VM for M candidates in the discrete setting. Each person gives V1 a score to their top vote, V2 to their second vote, and so on. We take the sum of the scores, and the person with the highest score wins. So for Borda, it is M-1, M-2 up to 0. And for plurality and key approval, it's 1, then 0, or K1s, then 0. Now let's talk about computing. So the point of voting rules, unlike the fairness ones, is that existence is always guaranteed. Like we don't need to argue about some approximation of quantile fairness here. Plurality winner always exists, but can be computed. That's the challenge. So for plurality, we can say each person approves the policies that have the highest score for them, highest return for them, and then the winner is the one with the highest number of approvals. And surprisingly, while counting plurality votes is very easy in the discrete setting, in the continuous setting, we show that you cannot even approximate it up to a factor of root n. And n is the number of individuals, the size of the population. And we can also redefine key approvals like alpha approvals. Everyone approves their top alpha percentage of the polytope, like top alpha quantile. And then again, we want a policy with the highest number of approvals. But we show that for alpha between 7/8 and 1, computing one such policy is NP hard. And for alpha equal to 1, we get plurality. We just saw that it's even hard to approximate. But for small values of alpha, like less than 1/E, as a corollary of the quantile fairness, we know that a policy exists that is in the 1/E quantile of everyone, So, and we can somehow compute it. So there are some interesting things going on with this value of alpha. But maybe more interestingly for Borda, for the Borda count rule, I mean, you can interpret Borda as m minus rank. This score is this, for rank k is m minus k. And in the continuous setting, we can also have this inverse rank or the quantile defined as follows. And then we just want to maximize the sum of these inverse ranks. So we want to find the policy that maximizes the sum of fi's. We couldn't show hardness, but our guess is that it's hard. Like if you take this polytope and then plot this inverse rank based on the expected return, it's going to look like an S-shaped function. So this f is somehow sigmoidal on this domain of occupancy polytope. And we know that from the result of, I hope I'm pronouncing correctly, Udall and Boyd, that maximizing sum of sigmoids is hard. We couldn't show Borda finding Borda winner is hard in our setting, but it suggests that it's going to be hard. But at least suppose that the optimal one, the maximum Borda score, appears in the concave region of all agents. So if it is ranked very high, like for everybody, then we can probably use, we can use convex optimization to get close to the optimal Borda count winner. And I'm ready to conclude. Like in summary, we started from AI alignment and reinforcement learning with multiple individuals and reward functions. By taking this state action occupancy polytope as a space of alternatives, we adapted some ordinal aggregation methods from the discrete setting to the continuous setting. And I think for future directions, we need more algorithmic advances that scales these approaches beyond like a few thousand agents or states or actions. And additionally, this is very interesting to explore this strategic behavior like the Gibert, an equivalent of the Gibert-Satterthwaite theorem for this setting. And we can also extend it to the online reinforcement learning setting where we don't have the full information of the environment. And yeah, thank you for the attention and happy to take any questions.
All right. So to the audience, if you have any questions, you can either raise your hand and ask the question directly, or you can post the question in chat. Okay. So, I mean, you can here now in the Q&A period, you can just directly raise your hand. Meanwhile, I have a question that I'll ask. So here kind of you try to simulate the ideal approach of voting over policies. And I was wondering, like, what happens if you let individuals just vote over what to do? I mean, a lot of times kind of what we see out there in the real world, that if we are in some state, and if we want to, in the department, for example, like every time a question arises, we vote on that question, right? We don't think about our entire policy of how we are going to govern the department over the next kind of 20 years and then like vote over that policy, right? So how bad or good do you think would it be if we just let agents vote over each individual state and what probability distribution over actions to choose in that state, ignoring the MDP structure at all, and just I don't know how you want them to vote over each state. Maybe they just like provide their reward functions in each state, and you aggregate these reward functions to just find. So kind of running a separate election on each state. How good or bad do you think would it be empirically?
Okay, empirically, I cannot comment on that. That's a hard question. But an very interesting point. Okay, so if we take planning out of the policy, then in worst case, probably like if we have two routes at the first, like someone goes to doom and some goes to heaven, like we are missing on the heaven and all the next actions would be doomed. But we know as a fact that we can have not Markovian policies that are optimal. Like if you're at any state, regardless of the previous history, you could have determined the optimal action, like there is a Markovian policy that is optimal, but yeah, it should be difficult to find that on the fly. Like in hindsight, we can say that it could have been Markovian and without looking at the past decisions, but yeah, but I think it's a very interesting, like, theoretical question. Like, it looks like the price of, I don't know, ignorance, or that type of notions that we have.
Right. I have another question if nobody else has a question. So I guess like one way to take the MDP structure into account would be to use some kind of like a top only voting method where each agent just submits one of their optimal policies. And I think like the plurality was a problem because each agent could have many optimal policies, and then you
Yes.
somehow needed to take that into account. But what if you let each agent just submits one of their optimal policies and then aggregate these optimal policies and optimal policies in some manner? Again, like just your judgment as to like how good or bad would this be in practice?
Yeah, like I think one easy way to see it is like we can have these two edges, and if you, I mean, there is one thing that is optimal for both of us, but maybe if you report your top policy as something else and I report it as someone else as some other policy, then we're going to lose utility, both of us. Like we're using on a lot of options that could have been beneficial to us instead of just finding the best out of this and not very smartly selected policies. Like yeah, I think, I mean, the downside would be that we could lose a lot of utility.
Oh, there's a Marcus. Do you want to go ahead?
Yeah, so well, there's also a question in the chat, but I guess I'll go first. So you've motivated this as an AI control problem, and it's because there's a literature on modeling AI control problems in terms of Markov decision processes. But I mean, in fact, I think that the application is much more general, because one can just imagine any sort of like iterated social choice setting where, you know, society is making a sequence of decisions over time. And we have to aggregate the preferences of voters somehow on these decisions. Now, one of the key features of your model, which distinguishes it from the prior literature on kind of social choice with Markov decision processes, is that you insist on this purely ordinal framework with no interpersonal comparisons of utility. As I understand it, that's kind of one of the key moves that you make, and that's what motivates a lot of this investigation of these different fairness concepts and voting rules. So I guess one question I would have is, if one was interested in maximizing a utilitarian social welfare function over time, according to some system of interpersonal comparison weights, then one could investigate the question of I guess what in computational social justice is called distortion, right? So in other words, basically like by how much do you fall short of the utilitarian optimal ideal? Now, for this question to be well posed, of course, you'd have to pick some weights. So, I mean, one way to put the question is, you know, what is the set of weights which minimizes the distortion? And if the set of weights that minimizes the distortion is kind of close to zero, then what that means is that even though you're purportedly using purely ordinal data, in fact, what you're doing implicitly is maximizing utilitarian social welfare according to some set of weights that somehow is implicitly defined by this ordinal aggregation rule, right? I don't think that's going to happen. I think the minimum distortion is not going to be close to zero, but nevertheless, I think that that's an interesting question to look at. So have you looked at that question?
Yeah, that's an amazing point. And I mean, I have worked on the distortion literature, and it was very interesting to hear that. Okay, so about maximizing weighted welfare, I mean, in the end, wherever we are ending up in this polytope, it's gonna be, I mean, okay, we should try to be Pareto optimal always. Like we will be, whichever point that these would give us, these solutions would give us, we can try to find Pareto improvements over that, and always report that Pareto optimal point in the region that is dominating this point that we found earlier. So at least with respect to that weight, it's gonna be optimal. But
Sure.
yeah, if we have like a uniform weight, then because we maximize because this point that we found is paratoptimal with respect to
Ad
another
hoc,
weight, it's gonna
right.
have a
Yeah.
low distortion,
Yeah.
a bad
But
distortion.
not that hot, because then you're picking the weight after you've identified the Pareto optimal point. You're
Yes.
picking the weight that rationalizes that Pareto optimal point, which is
Exactly.
that's a nice move. But I mean, yeah, obviously having a uniform weight would be more interesting, right?
Yeah, but yeah, that's a very great question. Like, how would this affect distortion? I'm sure that is bounded from below by like a factor of n, because we are at least maximizing someone's utility.
Right.
And if we assume that people have similar ranges of utility, then it would be bounded by that. But not sure if we can get better than that. But yeah, excellent question.
Okay, thank you very much.
Thank you.
All right, Clemens, do you want to unmute and ask your question?
All right. I mean, this is just, it just came to my mind because I was working on the Tukey median, and there are contexts in which the Tukey median seems to be the right aggregation rule. It's a tops only aggregation rule, and it is very good if you assume that people have convex preferences. I'm not sure whether this makes sense in your framework, but there are frameworks in which at least we find, Klaus and I, that the Tukey median is just the right aggregation method to use. And there are some formal similarities. I'm not sure about interpretation, but there are formal similarities between what you do and what we do, where we have just a usual policy space where you just have an optimal policy and you want to aggregate optimal policies, assuming that you only know the tops of the voters and assuming that they have convex preferences. And then it turns out that the Tukey median has very good properties. Just a
Should
remark.
look into that. Yeah.
Just a remark. I'm not sure whether it's useful also in your context, but I can imagine it is.
That was a very interesting point. I should look up any references.
Yeah,
I
shall be glad to send you the reference that I have in mind.
Okay, that's awesome. Yeah, thank you, Clemens.
All right.
All right, there are no more questions. So let's thank the speaker once again. And that's the end of today's seminar. Thank you everyone for joining. And then we'll return next month on February 26th, where we have Laszlo Vig and Matthias Greger presenting. All right, so hopefully see you all next month.
Bye.